Okay, for this video, we'll be going through kinematics, success criteria E, G, and H. Okay, so success criteria E is plot and interpret a velocity time graph for motion in one dimension. Okay, so it's either going forward or backward. This is one dimension, right? Success criteria G, deduced from the shape of a velocity time graph when a body is at rest, which means not moving, or when it's moving with uniform velocity, uniform acceleration, right? Moving with non-uniform acceleration. And success criteria H, calculate the area under a velocity time graph to determine the displacement traveled for motion with uniform velocity, right, or uniform acceleration. Okay, so in this part, these two are the important concepts. The gradient of a velocity time graph gives the acceleration. That means the gradient represents acceleration in velocity time graph. Okay, can you recall for displacement time graph? Displacement versus time. Okay, the gradient actually represents velocity. Okay, but for velocity time graph, the gradient represents acceleration, and this is a very important concept. So whenever you see a velocity time graph, most likely will ask you to calculate the acceleration, which you can derive from interpreting from the gradient of the graph. Okay, so this is the first concept that's very important. So for the second concept that is very important is the area under the velocity time graph gives the displacement. Okay, sometimes you may not be given velocity time, you may be given speed time. Okay, if we are given speed time, then it will give us the distance, right, being the scalar and vector. Okay, so let's try with by looking at this graph. So always read what kind of graph you are given. Okay, so we are given velocity time graph. So the two concepts that we need to know is the gradient gives the acceleration and the area under the graph gives us the displacement of the object. Okay, so there are a few stages here. Let's look at stage A. Okay, for stage A, we see that the gradient is actually 0. Okay, the gradient is 0. Why is it 0? Because it is flat. Let's recap some of the concept of gradient. So this is a positive gradient, this is 0 gradient, and this is negative gradient. Okay, so they are all drawn with straight lines. Okay, so they are constant values, but for this flat line, we will say that the gradient is 0. Okay, for this upward sloping line, we will say that the gradient is positive. For this downward sloping line, we will say that the gradient is negative. Okay, but they are all drawn with straight lines, so they are actually constant gradient. Okay, later on I'll go through what is a non-constant gradient. So for this particularly, we do not say that the gradient is constant, rather we say that the gradient is 0 because it is flat. And what does the gradient represent? The gradient represents acceleration. Okay, the gradient represents acceleration, therefore the acceleration is 0. And bear in mind that the velocity is 0 as well. You can actually read off from the y-axis that the velocity is 0. So there won't be any distance and there won't be any displacement, because if the velocity is 0, this thing can't move, right? Then we go to B, we see that it is actually a straight line. It is upward sloping, so it is a positive gradient. It is a positive gradient. And what does positive, what does gradient means? It represents acceleration. It represents acceleration. Now, for this part, for B, the velocity is actually positive. Okay, so B, the velocity is positive, right? And the gradient is also positive. So both are positive, right? Velocity is positive, the gradient is also positive, which means both are pointing in the same direction. Therefore, there must be acceleration, which means the object will speed up, or the velocity will increase. And do we see that? Yes, we see that the velocity actually increases from 0 to 8, right? From 0 to 8. So the velocity is increasing. But how is the velocity increasing? Now we look at the shape of the line. The line is a straight line, therefore it is a constant gradient. So the velocity actually increases at a constant rate. Okay, velocity increases at a constant rate. So it is constant positive acceleration, constant increase in velocity, or increase in velocity at a constant rate. Let me write this down. Velocity increases because there's acceleration at a constant rate. Okay, velocity increases at a constant rate. Now we can actually calculate the area of the graph, under the graph. So you see that the area actually takes the form of a triangle. So the area will then be half base times height. So the base is actually 2, the height is 8. Therefore, the area is 8. Why do we need to calculate area under the graph? Because the area under the graph represents the distance traveled, or the displacement. So the distance traveled is 8 meters, the displacement is 8 meters, because we started off from 0, right? So now it has traveled 8 meters in the positive direction. So the distance traveled is also 8 meters. Okay, so you can in fact also calculate the acceleration, right? Because this is a constant acceleration. So it's 4 meters per second square. Now we look at C. Okay, let's examine the gradient. The gradient again is 0. But what does the gradient represent? The gradient represents acceleration. Therefore, the acceleration is 0, right? So is it not moving? Which is not true, right? Because it's actually moving with a constant velocity of 8. Okay, constant velocity of 8. Now, is the velocity positive? Yes, it is positive, right? But because there's no acceleration, so we will move with a constant velocity of 8, which means it's still traveling in the positive direction. Okay, now how about the distance traveled? Let me clean this. The distance traveled is the area under the graph. So we have this constant velocity from 5 to 10 seconds. That means my base of this rectangle is 5, my height is 8. So if I were to calculate the area for this rectangle, it will be equals to 40 meters. So that is the distance traveled. But now if I were to ask you how far is it displaced from the original point, remember we went through A, B, and then C, right? So at A it wasn't moving, so the same displacement, no displacement rather. For B the displacement was 8, right? Because the distance traveled was 8. For C the distance traveled was 40, therefore the displacement is 8 plus 40. It is now 48 meters away from the starting point. Okay, and also you can actually calculate for the acceleration, but you don't need, right? Because it's 0 gradient. Okay, now we look at D. Okay, we look at D. Let's clean this out a little bit. Okay, for D we see that the velocity is positive. Velocity is positive, but the gradient is negative, right? Which means they are in opposite direction. So if it's opposite direction, it means that it will decelerate. It will decelerate. Okay? When they are in the same direction, positive and positive, they will accelerate. If it's positive and negative, it will decelerate. Okay? And isn't it true? You went from 8 meters per second all the way to 0 meters per second. That means your speed is decreasing. your speed is decreasing. Okay, so we will say that the object is moving with constant negative acceleration. In this case, it's constant deceleration. Is it still moving in the positive direction? Yes, because the velocity is positive, just that it is slowing down. So can we calculate the distance traveled so that we can find the displacement? Yes, because it is actually a triangle. It's the area under the graph with the y-axis, with the x-axis as the reference. Okay, so it is above this. So we must always use the graph and the x-axis to frame the area. Okay, so the base of the triangle is 1, the height is 8, therefore half base times height, it has actually moved a distance of 4 meters, but the displacement from A to D, right, it will be 8 plus 40 plus 4, right? We are continuing this story. So we have a total displacement of 52. And this part, velocity decreases from positive 8 to 0, okay? And you are actually able to calculate the acceleration. Take note, the gradient is actually negative, right? This is positive gradient. I'm repeating this. This is 0 gradient, and this is negative gradient. So the acceleration is actually minus 8 meters per second square, or we can say that the deceleration, okay, is 8 meters per second square. For deceleration, there is no negative deceleration. Okay. So can we go to next part, which is E? And let me clean this a little bit. You can review in the video. Okay, so for E, right, from 11 to the 12 seconds, the velocity is actually negative. Okay, it's negative velocity. Why is that so? Because it is at the bottom of the x-axis. The velocity is negative, right? It went from 0 to minus 8. Okay, so some of you may think that, oh, from 0 to minus 8, isn't it decreasing velocity, right? But do take note, the negative only tells us whether is it moving in a positive direction or negative direction. So in fact, for E, right, it is going back to the in the opposite direction. It's going back towards where we started. Okay, A, B, C, D, or B, C, D, whereby there's positive velocity, it is moving in a positive direction. But E, it is negative velocity. It doesn't mean that it's not good. It just means that the direction is towards the negative direction. Means it is actually U-turning, right? Once the velocity reaches 0, it actually U-turns and go back in the negative direction. Okay, so now we compare the gradient with the velocity. Velocity is negative. The gradient is also negative, right? So negative and negative, the velocity is negative, the gradient is negative, which means the acceleration is negative. Both are in the negative direction. This will actually mean that the object is speeding up or accelerating. Okay, and if you look at the values of the velocity, it actually went from 0 to negative 8. This negative, again, I must stress, it doesn't mean that it's not good. Okay, positive doesn't mean it's good. It just tells us the direction. If we look at the numbers, it went from 0 to 8, although in the negative direction, it is actually speeding up. It is actually accelerating, but now it's accelerating in the opposite direction, towards the left, if we choose positive to be right. Okay, so the object is moving with constant negative acceleration in the negative direction. So it sounds very, I made this set of notes quite a long time ago, but I think it is easier for us if we look at the sign of the velocity and the sign of the gradient, which is actually the acceleration. If they are both in the same direction, negative and negative, it means object speeding up. So actually the object is accelerating. So the velocity is increasing. It is increasing, all right, at a constant rate. This is for E. Okay. Let us calculate the distance under the graph. So again, we use the x-axis to frame the area. So this is actually the area under the graph. Okay. So again, this takes the shape of a triangle. So the base is 1. The height is -8. Okay. So actually, we can just calculate it as the distance of 8 meters. Okay. The distance for E, is half times base times height. So it is 4 meters. Right. Because for distance, there's no positive or negative. There's no direction involved. Right. So it is actually still moving, although it is moving in the opposite direction. So in this case, the displacement, we need to minus off this distance traveled, because now it's traveling back to the original position, right, to the left. So the displacement is actually 52 minus 4, which is 48. Okay, then I hope you understand this. The velocity increases from 0 to -8. Again, the negative doesn't mean that it's bad. Okay, it's actually an increase if you look at the numbers itself. And the acceleration is actually negative. But why negative? Because it's in the negative direction. Okay, next is your F. So again, F, take note that the gradient is 0. Therefore, there is no acceleration. Okay, because gradient represents acceleration. So it is moving with a velocity of 8, but it is in the negative direction. Are we able to calculate the distance traveled? It is again this area, which is framed by the x-axis and the shape of this graph, right? So over here is 5 and here is 8. So the distance traveled over here is actually 40 meters. But because it is moving in the opposite direction, therefore, now my displacement is only 8 meters from the original. Okay. Okay, let's look at G. Okay, for G, the velocity, it is negative, right? Because it's below the x-axis. For G, velocity is negative. Now, the gradient is actually positive. So they are having opposite sign, right? Their sign is opposite because velocity is negative and gradient, which represents acceleration, is positive. So they are opposite, right? So if they are opposite, it means it is slowing down. Slowing down, or it is decelerating. Okay? Or we can say that the velocity is decreasing. It went from -8 to 0. -8 to 0. Right? So you may think that, oh, -8 to 0 is actually good, right? You initially have -8, but now you become 0, so you are increasing. But we just look at the number itself. It actually went from 8 to 0. How about the minus? The minus again tells us that it is in the negative direction. Okay, so it is actually decreasing in velocity, right? And we can actually calculate the area here, which is 2. The base is 2. The height is 8. So the area is 8 meters. Okay, so the distance traveled is 8 meters, right? And if we deduct everything, okay, it is the displacement for G is actually 0. It's back to its original starting point. Okay, so this graph is designed such that this area, right, corresponds to this. Okay, this corresponds to this, right? And this area corresponds to this. Okay, it's just that over here it is moving in the positive direction. Over here is moving in the negative. So in the end, they cancel out, and therefore over here the displacement is equals to 0. but the distance you have to add up. Okay, once you have walked a certain distance, you cannot minus off. You cannot unwalk that distance. So the distance traveled, you need to add everything together. Okay, so you have to add 8, you have to add the 40 for each stage. Okay. Yep. Let's look at H. Okay, let's look at H. For H, okay, let me erase this. For H is from 19 to 22 seconds, okay? And being at the bottom of the x-axis, below the x-axis, that means the velocity is negative, okay? And the gradient, which represents the acceleration, is also negative. So you take note that both are in the same direction. They have both the same sign. Therefore, in this case, the object is actually speeding up. Okay, the object is speeding up. Okay, it actually went from 0 again to 8. Okay, it's actually speeding up. Okay, but it's moving even further back. Okay, that means it has gone past its original position. Okay, so it's actually speeding up, right? But if we were to look at H, it is not a straight line. It's actually a curve. Okay, so we can actually say that it is accelerating, but we can do even better. It is not just accelerating uniformly. It is actually a non-uniform acceleration. So then we have to examine the shape. Okay, the shape of the curve for H. Okay, so very simple. We just break it up into two parts. From 19 all the way to here, 19 seconds all the way to here, this part is gentle. And over here, this part is steeper. That means the shape went from gentle to steep. Okay, that means the gradient actually increases. The gradient increases. And what does gradient represent? The gradient of a velocity time graph represents acceleration. That means the acceleration increases. Okay, now how does this translate to the velocity? Whenever we say there is acceleration, we know that the velocity increases. So this is for this part. Acceleration, velocity increases, right? But now your velocity is actually increasing, right? So how do we account for that? That means that a velocity increases at an increasing rate. Okay, why do I put rate as capital letter? Because a lot of times students will put the velocity increases at an increasing speed. At an increasing speed. They try to use speed to replace rate. This is not very accurate. Okay, so use rate. Right? So the purpose here is to tell us that the acceleration increases because I can have constant acceleration. If I have constant acceleration, how does it translate to my speed? The velocity increases at a constant rate, right? Because I have constant acceleration. But now if you look at the gradient for H, the gradient is actually not constant. That means the acceleration is not constant. So if you just say it's not a constant acceleration, for pure physics students, I'm afraid you have to go one step higher. Okay, or one level higher. In this case, you have to examine the shape of the graph. The shape shows that it went from gentle to steep. Therefore, the gradient increases. And what does gradient represent in velocity time graph? It represents acceleration. That means the acceleration increases. But if I were to ask you, how does the velocity increase? You know that acceleration means velocity increases, right? But what about acceleration increases? So the velocity increases at an increasing rate. Okay? Then we go very quickly to I, which is the opposite of it. Okay, let me clear this up. Okay, so for I, the velocity, it is negative. Okay, for I, velocity is negative. Okay, and the gradient is positive, right? Because this way, it is positive. And a gradient represents acceleration. So before you say whether it is accelerating or decelerating, look at the sign. If the velocity and gradient are both having opposite sign, that means it is decelerating. Okay, that means the velocity, very simply, means is decreasing, right? So I say this again. We first look at the velocity. The velocity is negative because it's below the x-axis. This one you agree. The gradient is positive because it's sloping upwards as the time goes from 22 to 25. Therefore, it is a positive gradient. Now we look at the sign. Velocity and gradient, they are opposite sign. So instead of saying straight away is accelerating or decelerating, you need to decide whether they are same sign or different sign. Since opposite sign, different sign, it is decelerating. But decelerating straight away means velocity is decreasing. Look at the value. It went from -8 to 0. Just by looking at the value of 8 to 0, the velocity is actually decreasing. Right? So it is true, it is decelerating. But is it decelerating at a constant rate, increasing rate or decreasing rate? You would have to see whether is it a straight line. Obviously, it's not a straight line, right? It's a curve. So now we need to look at the shape. Okay, just like when we are doing for H, over here, divide into two parts. Over here is steep. Over here is gentle. So the shape is from steep to gentle. Okay, it's from steep to gentle. That means the gradient is decreasing. Okay, now what does the gradient represent? We already know that it is decelerating, right? So the deceleration is decreasing or decreasing deceleration. Now deceleration means velocity decreases. Okay, so the velocity actually now decrease at a decreasing rate. Okay, so you might want to look through the video again, right? So I think it's mentioned in H and I. Okay. Okay, so take note, negative velocity just means that the direction of travel is opposite from the direction of travel when it is positive velocity. Okay, and also distance travel in H and I, which is actually the area under the graph, cannot be calculated because the object was not traveling with constant acceleration or constant velocity. Now, what's the comparison between displacement time and velocity time graph? So they give us a scenario from A to B. Okay, the car accelerates uniformly from rest. That means it's a constant acceleration, which means the velocity increases at constant rate. Okay, but they want us to compare between displacement time graph and velocity time graph. So since we have written this down, can we check that for velocity time graph, right, the velocity actually increases at a constant rate? Why? Because this is a straight line. Okay, so straight line means constant gradient. Constant gradient means constant acceleration. So this part okay, but how do we translate it to displacement time? Now, what if you want to translate to displacement time? You need to know what is important. The gradient of displacement time represents velocity. Okay, So actually this section is very important because sometimes the question will ask you to draw a displacement time graph and translate it to velocity time, or they give you a velocity time graph and they ask you to translate it back to displacement time. So in order to do that properly, you need to know what is important for each graph. For displacement time graph, the gradient represents velocity, but because my velocity is increasing, right, therefore my gradient must be increasing. Let me put it down. The velocity is increasing, right? So if I were to translate to displacement time graph, whereby the gradient represents velocity, if velocity is increasing, then I replace velocity with a word called gradient. Gradient will then be increasing. If gradient is increasing, that means it goes from gentle to steep. So do you see that from A to B, this part over here is gentler and over here is steeper. So this is how you translate from velocity time to displacement time. Okay, let's look at the next scenario, whereby the car moves at constant velocity. Okay, constant velocity. Okay, I hope you are annotating this on your notes. Constant velocity, which means acceleration equals to 0. Okay, so how would that look like in a velocity time graph whereby the gradient represents acceleration, right? So therefore, if the gradient is equals to acceleration and acceleration equals to 0, if acceleration equals to 0, that means the gradient equals to 0, thereby we have a flat line, right, whereby I have a 0 gradient. That means over here it is constant velocity. So again, how would that translate to displacement time graph whereby the gradient represents velocity? Okay, so if I have constant velocity, that means in a displacement time graph, my gradient will also be constant. So it will have to be a straight line. Okay, straight line. So this will tell me that there is constant velocity. All right. Now we go to the last part. The car decelerates uniformly to a stop. That means it is constant deceleration. Okay, so the velocity over here is positive. Now in order for it to be decelerating or having velocity decreasing, the gradient must be negative, right? Opposite sign, right? So that means over here velocity is decreasing. I will say velocity decreasing at constant rate. But what does the gradient in a displacement time graph represent? It represents velocity. That means if here velocity is decreasing from C to D, in a displacement time graph, the gradient, which represents velocity, will also be decreasing. Let's see. So the gradient, again split up, it will not be a constant straight line, it will be a curve, whereby my gradient decreases because my velocity is decreasing at this point in time. Okay, so we see that compare, here is steeper and here is gentler. So steep to gentle, the gradient decreases. What does gradient represent? Represents velocity. Velocity decreases, right? And it is like what the story suggests. Okay. Now, this is another comparison, but this time speed time graph versus velocity time graph. So again, speed is a scalar. There is no direction. Okay, there's no direction. Okay, velocity is a vector. There is direction. Okay, so we look at the first speed time graph, or rather we look at this ball. Okay, the ball is tossed vertically upwards. Okay, and then it falls freely. We neglect air resistance. This will be covered later. And if we assign upward direction from ground as positive, okay, so if the ball is thrown upwards, in order to throw a ball upwards, you need to apply a force and you need an initial speed, which is our u, right? If the ball, you don't give it any speed, it will just stay in your hand, right? In order to throw it higher, you need to apply a larger force and a higher initial speed. Okay, but because they say there's no air resistance, so the only thing that's pulling the ball down when it's going up is actually your gravitational field. Okay, it's actually your gravitational force is pulling it down. So it will initially start at A, right, having a high speed depending on how much force you put in, and when it reach the maximum height, okay, the speed will be 0. So from A to B. Okay, and after that it will fall back down to earth, okay, and being pulled down by gravitational force, it will increase in speed. Okay, so it will reach stage C. Now what does area under the graph means? For speed time graph, it represents the distance. So this triangle A1 plus A2 will be the distance traveled by the ball. You can actually add them up, which is h plus h, because the height that it reaches is h. So it travels up h, it travels down h, so the total distance traveled is 2h. Now we look at velocity time graph. We say that upward direction is positive, so we give it a initial velocity of u, which is positive, right? When it goes up to B, maximum height, the velocity reaches 0, right? That's why a ball comes down. But once it goes up, it reaches maximum height, it will come down. Going down means it is negative. Going down means negative. Okay? That's why it goes below the x-axis, right? And it reaches C. Okay, so we can actually calculate the total displacement is actually A3 plus A4, which is A3, a positive distance, a positive displacement, but A4 will be a negative because it's in the negative direction. That's why the total displacement is 0. Okay, so maybe you can try G1, H1, and H2. Okay, and then later on I'll go through the answers. Okay, I hope you have tried G1. Okay, so the speed time graph of a motorist is as shown, which of the following deductions is incorrect. So we are looking for the incorrect deduction. So this is actually a speed time graph, so we always look at the axis first. Now before we attempt this graph, it's good to write down the concepts. The gradient represents acceleration. Okay, and area under the graph represents the distance traveled. Okay, so they say the velocity decreases uniformly. Is it true? It went from 10 all the way to 0, and this is a straight line, meaning it has a constant gradient. So this will make A true. Now the average velocity is 5 meters per second. Now is that true? Okay, we can actually calculate the area under the graph. Okay, so the area under the graph gives us the distance. Now this graph, the area is actually a triangle. So height of 10, base of 50. So the area is half times base times height, 50 times 10, so equals to 250. Now how do you find the average velocity? It will be total displacement, right? Because there's no change in direction, so the distance is the displacement over total time. Okay, so we'll get 250 divided by total time of 50, it will be 5 meters per second. So again, this is true. Now the distance traveled in 50 seconds is 250 meters. That is true. Now the deceleration is 5 meters per second square. We can actually calculate A equals to V minus U over T. the final velocity is 0, initial is 10 divided by 50. So we actually get negative 0.5 meter per second square. And because this is acceleration and it's negative, so we can take it that the deceleration that we calculated is 0.5 meter per second square, but it is not true because over here it's stated 5 meter per second square. So answer is D. Okay, H1, the diagram below shows the velocity time graph of a stone thrown vertically up into the air. So the initial motion is that it's thrown up. And if you look at the velocity, initial velocity, it is actually positive. That means up is positive. That means down is negative. So a lot of you actually ask me, how do we know whether up is positive, down is negative? Will it be given in the question? It is given as such in the question in the graph, right? Because the context is that it's being thrown up vertically, and the initial velocity is actually positive. Okay, so the stone is thrown up at time 0. Area x, this is x, represents a distance of 5 meters. So this is 5 meters. Area y represents a distance of 3 meters. Okay, so it actually went up 5 meters. It came down 3 meters. So assuming that air resistance is negligible, calculate the displacement of the stone from its initial position at time t. Right? So this is the starting point. It was being thrown up 5 meters positive. Then it came down 3 meters, right, over here. So what's the displacement? It's actually 2 meters away. Okay. Now H2 diagram below shows how the speed of two cars A and B varies over time. So again, speed time graph. The gradient represents acceleration, area on the graph represents distance traveled. Now, which of the following describes how the distance between the two cars changes between t equals to 0 and t equals to 14. So t equals to 0 is here, t 14 is over here. Okay. Now, the distance between the two cars. So take note that all the options cover distance, which is actually the area under the graph. So you can see that for A, right, because it's traveling with constant speed, therefore the area will always take the shape of a rectangle. Okay, but for B, it's slightly more complicated. It from 0 to 4 is actually not moving, right, because the speed is 0 and the area underneath is 0. All the way until 14, right, it takes the shape of a triangle. Okay, so that is for B. Okay, so how do we solve this? The distance between the two cars decreases at a uniform rate. What do you all think? Does it decrease at a uniform rate? Okay, so I need you all to think in terms of speed. Okay, if I have two people that are racing and two cars that are racing, and A actually started off first at a very high speed of 20, and it just runs with 20 meters per second. Okay, whereas B, you see that it's trying to increase the speed all the way to 20. So basically from 4 seconds all the way to 14 seconds, the speed is lesser. Speed of B is lesser than speed of A from 0 to 14 seconds. So if the speed is lesser, will it catch up with it? No. In order to catch up with somebody, okay, the speed must be higher than the speed of the person that he's trying to catch. But you see that from 0 to 14 seconds, there is no point in time whereby the speed of B is greater than A. So they will never catch up. So this would mean that the distance between the two cars does not decrease. It's in fact increasing, but it is increasing at a decreasing rate. Okay, so A is false. Now, distance between the cars remain constant, which is false again, okay, because the speed changes. Now, the distance between the cars increase at a uniform rate. it is again false. The answer is D. Okay, so maybe for this part, you all need to discuss among one another. Then when I can maybe show you another time. Okay, so this is all for this video.